All right, section 5.2. Hopefully this video records, that way I don't have to be sad like it was yesterday when my video completely failed. We're going to be starting our trig proofs, what I like to call a trig proof. Now realize it's not the kind of proof that you saw in geometry. So it's not going to be a column proof. It's not going to be a paragraph proof. No, it's going to be more like a, well, I'm just going to write this equals something else, and I'm going to use an identity to get to the next equal sign. So it's actually a lot of what you saw me doing yesterday, simplifying things in this manner, and we just call that a trig proof. Now you're going to find that the struggles with trig proofs are pretty much the same struggles that students have with geometry proofs, and that is, how do you even know where to start often, right? Well, in geometry, that question's pretty easy because normally you've got a picture and you go, well, what does the picture showed you to be true? And what do you know to be true just by looking at the picture that wasn't mentioned? Basically, that's where every geometry proof starts. The trig proofs are a little bit different. Trig proofs, you go, well, how would I know to do it in that method? The answer is you don't know 100%. Much like this question, honestly, I haven't done this question since probably last year when a student asked me about it. So how did I know that I should have converted this to sine over cosine and this to cosine over sine? Because like I was explaining before I started the video, it's a bag of tricks and patterns you get used to seeing, honestly, over time. So as I go through these things, I will tell you, when you see this kind of setup, most of the time this is your plan of attack. But I'll be real with you. There have been plenty of times where I've been doing a trig proof and I was traveling down logic that was not incorrect. But then I got to a point where I couldn't take it any further. And when you hit a brick wall, you know what you do? You give up. No, I'm kidding. What you do is you go, okay, that didn't work. Let me try to do something else that I know I'm allowed to do. And you approach the question in a completely different manner. You might have to hit 2 or 3 brick walls before you get a question right. You just have to have fortitude. Don't give up on it. Just realize if you took it down a path that took you nowhere, it doesn't mean you were wrong. It just means you took the wrong path. So go try something else. That's what you're going to have to do when you're doing these questions. Okay? How did I know to start there? Honestly, experience, and because usually this trick would work. Things like that. That's how you know. All right, so let's see what we got going on here. Let me grab my version of the notes just so I don't make a gaffe. All right. Now this first one's an algebra question. It just says, hey, prove algebraically that this setup equals 2. Generally what that means is don't do anything with this side, generally. It usually means start on the left side and work until you land on the right side. So just looking at this, algebra, there is more than one way to start this question. There's an easy way and there's a hard way. But there are 2 different things that I instantly see I could try. Thing number 1 that I could instantly try, I could attempt to find common denominators. That is often something you need to do. When you see pluses and minuses between fractions in trig proofs, often you're looking for a common denominator. And that is how I would have started this question if I hadn't seen thing number 2. These 2 objects factor. Again, these are patterns that you look for. So yeah, I would have gone with the common denominator if I hadn't instantly seen that I can factor and that something will cancel when I do that. So that's how I'm going to start this question. X squared minus 1 is the difference of 2 squares. It factors to x plus 1 times x minus 1. Same thing happens on the right side. Oops. Notice I didn't write equals 2. We don't know that to be true yet. We're just going to keep saying, okay, well, this is this, is this, is this, is, oh, and at the end it's going to equal 2. If you write equals 2 at the very beginning here and you keep writing equals 2, that means you've already assumed that it's true. You're not allowed to assume something is true in order to prove it's true. It's like, hey, Mr. M, prove to me this is a table. And I go, okay, well, first let's start by assuming it's a table. Done. You know what I'm saying? Like, that's bad logic. You can't do that. So we never just assume that this 2 is a truth. We work our way to the 2. We can cancel. Those cancel, and those cancel. And what it leaves me with is x plus 1 minus x minus 1. That is an awful x minus 1. That means you're subtracting the x and this negative 1. It's almost like you're distributing. You're subtracting x and you're subtracting negative 1. And hey, look at that. X minus x is 0, but 1 plus 1 is 2. Ta-da! Because I worked my way through logic and landed on 2 at the end, I know that, yeah, this original setup did equal 2. Yeah, but we distributed minus x minus negative 1, which is where the plus is coming from. There we go. So algebra's out of the way. I gave you 1 or 2 of those in the homework. That's easy peasy, lemon squeezy. We do need to get onto trig, though. So we go here. All right. Again, most of the time, I bet you 90, 95% of the time, you start on the left and you work until you land it on the right. You manipulate it until you get the thing on the right side. The benefit of this is you already know it's true. You've been told it was an identity. That means there must be a way to get to here. There must be a way. Now, if we called an Uber, usually I say taxi, but times are changing. If we called an Uber and I hop into the Uber and they go, where do you want to go? And I go, take me to my grandmother's house. Does the Uber driver just start driving? No. No, of course not. Why? Where does grandma live? Yeah. Okay, but here's the thing though. This person does know I'm going to grandma's house. So this person knows now I'm going to grandma's house. And they go, okay, how do I get there? You tell them or you give them the address, whatever. The point is, they do know where they're going. You know where you're headed. And you're allowed to keep that in mind. You're always keeping this goal in mind. Okay, I somehow need to get to a secant x, cosecant x. That's 1 over cosine, that's 1 over sine. So I'm on the hunt for a 1 over cosine, 1 over sine at some point. And I know that. I'm trying to force this to give me what I just said. Let's rock and roll. Tangent x and cotangent x have no exponents. More often than not, and this is not a 100%, it's just more often than not. When there are no exponents, you're not going to be hunting for Pythagorean identities. Are there times where you could manipulate? Yes, there are. I'm going to say there are. But more often than not, you don't. More often than not, when you're dealing with things that can be written as fractions, you write them as fractions and see what happens. Tangent x is sine x over cosine x. And cotangent x, being its reciprocal, is cosine x over sine x. Then you can put 1 over sine cosine. See, what we're looking for here is a common denominator. You can't just add fractions unless they have a common denominator. So what we will do is we will multiply the top and bottom of this by sine, and we will multiply the top and bottom of this by cosine. What just happened to my brain? I wrote the wrong thing. Sorry. Like that. If you completely ignore the scribble marks there, what you're going to end up with is a common denominator of cosine x sine x. Remember what we were hunting for? We were on the lookout for a 1 over cosine, 1 over sine. Oh boy. I already have a cosine and a sine in my denominator. My red flags are going off. Let's see what happens on the top of this fraction. Sine times sine is sine squared. And cosine times cosine is cosine squared. And oh my goodness. Sine squared x plus cosine squared x, which is 1. The Pythagorean identity. So there it is. 1 over cosine, 1 over sine directly equals secant x times cosecant x. Boom. Is it always that easy? No. But again, if you have no exponents and you have trig that can be written as fractions, usually that's the plan of attack. Not always, but usually. That's the best I can tell you. Questions, comments, concerns about that one? Not too bad, right? Not too scary.
What the heck?
Oh, oh. He's spazzing out. So the last couple days, Max has been asking me what the test would look like. You'll have things like this on the test where it goes, hey, this equals one of those two things. It is our job to figure out which one it equals. Okay, this is a little bit tougher. You hopped in the Uber and you said, well, I know I'm either going to grandma's house or grandpa's house. Grandma and grandpa just couldn't make it work. So we know we're going to one of two places. So what do we have to do? We have to rely on our smarts. Honestly, that's just what we're going to have to do. So go, fine. The textbook authors intended for you to pick the match up front and then confirm it with a proof. But the only way I could think to do that would be with a graph. I'm not trying to do that. So what I'm going to do, because you're not going to have your graphing calculator on the test, is I'm just going to dive into it and start manipulating it using trig, hunting for identities until I land on one of these. Okay? Wo bist mein Pen? Here it is. All right. Again, I see absolutely no exponents, but I do instantly see two fractions. They do not have a common denominator as it sits, but I could make them have a common denominator, couldn't I? This is often the plan of attack.
Don't just then multiply the secant by -1?
Well, what you want to do is you want to treat this as one object, because when you're looking for common denominators, you're looking for things that are separated by multiplication. So secant x minus 1 is one object. Secant x plus 1 is a completely different object. They technically have nothing in common. The only way to get to common denominator is multiply them by each other's denominator. That's it. So we know it equals, let's see if I can do it this time without goofing it up. Multiply this one by secant x plus 1 on the top and bottom. And we'll multiply the other one by secant x minus 1 on the top and bottom.
Never how simplifying is harder than actually harder than solving that.
Yeah. All right. You know, normally we don't actually multiply the denominators, do we? We normally leave them factored in case something's going to eliminate somewhere. But again, we have knowledge, we're thinking ahead. Without doing the math, it's great if you could see that these are what's the word? Conjugates. And if you multiply them, you will get a difference of two squares, won't you? If you were to multiply these, you will get secant squared minus 1. Well, that sounds familiar. Secant squared minus 1. Isn't that one of my... Oh, that's right, yeah. It's one of my Pythagorean identities. Look, do I have them memorized? No. But I know that a secant squared x Pythagorean identity exists with a 1 in it. So maybe off to the side, I would quickly derive it if I didn't already know it, or you've kind of committed them to memory. But the point is, secant squared x minus 1 is one of the Pythagorean identities. So I will multiply them this time. Mr. M, but come on, how would I have known to do that? Okay, another way you would have known. Often the reason why we do not multiply our denominators is because we're hoping that something will cancel off the top, correct? That's the hope. Well, this is the thing. Look, if we don't combine the bottoms, let's just pretend they're separate for a second. Look ahead. You're allowed to look ahead. You're going to have, and why don't we just write it? Secant x plus 1, and then here's a plus. Nothing negative is being multiplied, plus secant x minus 1. The only way something would have canceled off the top of the bottom is after I combine like terms if I either had this blue thing or this red thing. But you're not going to, because the plus 1 and the minus 1 will cancel each other out. You're just going to have two secant x on the top. So boom, there you go, dead giveaway. Nothing was going to cancel as it sat on the bottom. You weren't going to be able to cross something off the top and the bottom. And that's another reason why I went ahead and multiplied them, because I can see ahead. That's very easy math. I can see that the plus 1 and the minus 1 are just going to cancel each other out, which means I will not be able to get either this statement or that statement on the top alone. So nothing will cancel off the top and bottom. I might as well go ahead and multiply them. And oh, wait a minute, that's right. Pythagorean identity. Secant squared x minus 1 is tangent x. Squared x, excuse me, tangent squared x.
Right. So how do you said to derive it? How do you derive it?
We derive it the same way we did a couple days ago. Flip back to it. You start with the regular Pythagorean identity, and if you're trying to figure out what's going on with secant, you create a secant by dividing all of this by cosine. See, if you divide by cosine squared, you get a secant here, which is what I did down here. This is how we derived the other ones. Divided everything by cosine squared. 1 plus tangent squared is secant squared. Subtracted 1 from both sides. Oh, secant squared theta minus 1 is tangent squared theta.
Yo, can we get an open note test?
No open note tests. I am going to give you guys a formula sheet, but it only has this Pythagorean identity on it. But you need to be able to derive the others. Well, this isn't finished yet, because we clearly haven't gotten to Grandma's house or Grandpa's house yet. Hey, notice that the two answer choices, there's no exponents, right? But there's an exponent here. Clearly something has canceled somewhere. But how? Okay. Remember, tangent is sine over cosine, right? We're good with that idea?
Yeah.
Okay. So let's say we have 2 secant x divided by sine squared x over cosine squared x. Ew, fraction divided by a fraction, right? Keep, change, flip, right? So instead of saying 2 secant x divided by, I'll say 2 secant x times cosine squared x over sine squared x. Exponents. Still there. Somebody tell me something else. Like a boss, McKinley steps in with the strong logic, big brain in it. Yes, secant x is cosine 1 over cosine x. So I will replace my secant x with a over cosine x. Now, that happens. And this allows me to cancel a cosine off of this one and one of my two cosines from here. That leaves me with a 2 cosine x over, and again, neither grandpa's house nor grandma's house has any exponents in it. So, oh, by the way, I think it's pretty obvious that the answer is this one because this is the one with a 2 in it. But still, we're going to keep going. Since there's no exponents in that first option, I'm going to write this as sine x sine x.
Oh, cosine.
Like that. And hey, what is cosine x over sine x?
Cotangent.
Cotangent. And what is 1 over sine x? Cosecant. The 2, and then cotangent x, cosecant x. There it is. Hooray, logic. You guys want to say anything other than, want to ask me any questions?
I mean, this is actually starting to make sense now.
That's good.
Will that make sense in a few hours when I do it?
Yeah, legitimately, the trig proofs, and I'm not the kind of teacher, it's like, oh, well, the more you do, the better you get. But this is one of those things like you just legitimately need practice. You need practice, that way you can get fast at the problem solve skills of where should I go from here. Is that a question, or he almost has a question. Yeah, what's up?
How did you get the two secant?
So the 2 secant x right here. So right here we were confused where it came from, right?
Yeah.
Because this plus 1 and this minus 1 cancel out, and I just get secant x plus secant x.
Oh.
Remember, secant x is a number of some sort, so I just have 2 of them now. That's where it came from. Cool? All right. All right. Now, again, the headings kind of cheat and tell us what to do, and this will be as far as we can get in the notes today. We will finish this one. And basically, there is no stopping point in the homework. The strong suggestion is get as far as you can before your brain starts to melt, okay? I'm going to start on the left. I'm going to work my way to the right. Oh, good. Well, now, hold on. You're not allowed to assume this side is true. If you start doing something to both sides of this equation, you have automatically assumed it's true. When we're proving that it's a true statement, you're not allowed to do something to both sides. Now, I know, but it says prove that it's true. This is just the way logic works. So we're going to start with cosine. I guess I'll use a t. So I'll make it a fancy t so it doesn't look like a plus sign. So this is our setup. Now I told you guys maybe 80, 90, 95% of the time when you don't have exponents, you are not hunting for Pythagorean identities. And this is usually a true statement because usually there is stuff that I could write as fractions and try to find common denominators. But this time there's just not. I mean, I could call this one over secant and this one over cosecant, but that is not going to help me. So I have to problem solve a way around that. Be like, okay, so what could I do? Again, if it hadn't said difference of squares, you would see that this is almost this, which equals this. That's just a Pythagorean identity by solving for sine or cosine by subtracting sine from both sides. That's all that is. And this was the thing that Briar was asking me about in the homework. She was noticing here that this was, I can't remember which was it. Was it this one, Briar? The bottom one? You said, or was it the top one? I think it was the top one. Is it 1 plus tangent squared is secant squared? Right. So she was trying to figure out how to make this say 1 plus tangent squared. There was absolutely no way. You could make it say 1 minus tangent squared pretty darn easy, though. And that's why I knew that that wasn't the go-to thing. If this had said 1 minus tangent squared, again, there would have been no way for me to get 1 plus tangent squared out of it. But when your Pythagorean identity involves 1 minus something, oh boy, you're in good luck. You're in good shape here because this is a difference of 2 squares. You can create these easily. Oops, there we go. I used a fancy I by accident in my sign. So sometimes creating Pythagorean identities is the move. Sometimes it is, and that was, so how did I know to do that? Well, because I only had one fraction, so there wasn't any finding common denominators. And sine and cosine are pretty much animals that you don't want to mess with much. You don't want to call cosine 1 over secant very often. You don't want to call sine 1 over cosecant very often. Occasionally it's needed, but it's rare. But every now and then, when you hear hoofs, it is a zebra and not a horse. Every now and then. That's not true. I've seen zebras in Florida, just not wild. Okay, so they were in a pen. Right here. We know that we're going to get a difference in 2 squares right there. It's going to be 1 minus sine squared t. On the top, you know what I'm not going to do? I'm not going to distribute. But why, Mr. M? Because I know my future. My future is going to end with a cosine t on the bottom with no exponent. I know that this is going to give me a cosine with an exponent. That means somewhere along the way, a cosine canceled. So I'm not going to distribute on the top. You are allowed to know where you're headed. You are allowed to keep that in mind. This thing down here, like we've already said, is directly a Pythagorean identity, does not need to be manipulated. It equals cosine squared t. And because they're separated by multiplication on the top, it allows them to cancel. Whoops. Right here. If that was a plus or a minus, no, it wouldn't be able to cancel. But because it's a multiplication dot, yes. This cost will eliminate one of those, leaving us with the right side of our equation, which is 1 plus sine of t over cosine of t. Pin drop. All done.